Okay, I got my calculator now. We're going to take and multiply 16 times 12 and divide it by 25. 16 times 12 equals 192 divided by 25 gives me 7.68 inches. Okay, on a test, that number is going to come out even. It'll be to the even inch or the even half of an inch. So if you get a number that looks like this on a test, you know you messed up. Take a look at it. It's either going to be 7.5 inches or 8 inches. It's not going to be a decimal. So you're not going to have to make this decision. So I'm not going to put that on a piece of paper and give it to somebody in the field. They don't even know what 7.68 is. So I'm going to change this to the most logical number, which is 8 inches. So we're going to have a slab that is going to be 8 inches thick. So that's the first step, is to get this number. Now I got to check it. If it works out that that's a good number, then I've got to go ahead and determine the steel. So we just did part A. Part A, determine it. Now we want to check it for flexure. Flexure, of course, is bending. So we've got a number, 8 inches. You also need this number. Don't discard it. That's used down the way a little bit. Okay, but 8 inches is our number. So it's check for flexure. The 1 foot strip. We got superimposed loads, live and dead, and we've got the weight of the concrete. Concrete, as you know, we've used in the past as being 150 pounds per cubic foot. So we're going to go ahead and go to letter C. Letter C says determine the factored load. The factored load, in your world, that is little w. Okay? This is the load per lineal foot. Okay, so I'm going to take it, and I'm going to take 1.2 times the dead, 40. And part of the dead, of course, is the slab weight. So I've got an 8-inch slab plus 8, change it to feet, multiply it by the unit weight of concrete, and I'm going to add to that 1.6 times live. Okay, if I do this, what do I end up with? I end up with clear. That looks like to be 140 times 1.2, 1.2 times 140, 168 plus 160 328 pounds per square foot. Now, we've got a problem. The problem is I told you that little w, its units are always pounds per lineal foot. If you look at this, it comes out pounds per square foot. Pounds per square foot, pounds per square foot. Feet times this, pounds per square foot. Okay, can't have it. So what do I do? Well, if our slab width is 12 inches, that's 1 foot. If it's 1 foot wide and it weighs 128 pounds per square foot, it weighs 328 pounds per foot. So I can do this. I can write 328 pounds per foot. The only reason I can do that is because my slab width is 12 inches or 1 foot wide, which makes pounds per square foot the same as pounds per foot. So there's my unit weight. That's what it's got to carry. It's got to carry itself. It's got to carry the superimposed dead and superimposed live. Go to letter D. We got to change load to moment. Flexure is bending. Bending is moment. So we'll go to letter D and MU, and you should recognize that equation. WL over 8, big W, L over 8, is little w ul squared over 8, which is ul squared over 8. U, 328. L, 16 feet squared over 8. That gives me that number. So 328 times 16 squared divided by 8. 10,496. There's 10,496 foot-pounds of moment. Okay, the next step says change that to MT by dividing by 0.9. That should not be anything foreign to you. MU over phi. So I'll take 10,496 and I'll divide it by 0.9 and I get 11,662. Okay, so that's letter E. So we're down to letter E. E, we've got it. Use balance section data on page 423, okay, which we've done already, to be used to find the, basically we're finding the depth required for bending, okay, effective depth, D. I already know T, so if I took the cover and half the bar diameter, I would have the D based on deflection. Now I'm going to find the D based on flexure or bending. So I'm going to change this. Our equation, if you remember, for, and I'm going to make this MT star, was RBD squared. And if you remember, the units were in inch kips. So I'm going to get rid of this, foot kips. So I'm going to take 11,662, I'm going to multiply it by 12. That gives me inches, and I'm going to divide it by 1,000. That gives me kips, so 139.95. So this is actually equal to 139.95 inch kips. Okay, that's just a conversion. Those two numbers are identical. Okay, the difference is the units. Foot pounds versus inch kips. So now, the next step says use that formula and find the D. So I'm in letter F. It's written a little different on this handout, but it's the same equation. So I'm going to put the 139.95 inch kips. R, it told you right there, go to page 423 to find R. My materials are 40 and 3. So I'm going to go back to 423. Okay, so 423 says at 40 and 3, I have an R equal to 1.149 KSI. 1.149 KSI. B, always 12. D, I'm going to make this D star squared. Okay, now what am I getting here? I'm getting the depth I need for bending. I already know the depth I need for deflection. Now, if the bending depth is less than the deflection depth, we're going to stick with that 8 inches and keep running. Okay? So let's do it. Let's take the 139.95. I'm going to divide that by 1.149. And then I'm going to take that and divide it by 12. Then I'm going to take the square root of that. And let's see, that's that guy right there. 5013055. I get 3.19 inches. Okay, they're telling me the effective depth of the slab for bending needs to be 3.19. Okay, I don't have a comparison yet because I've got a effective depth for bending versus a total thickness for deflection. I've got to change one or the other so that they're on the same platform. Okay, I'm going to change this guy. T equals 8 inches. T equals cover. Let's see. D equals T minus cover minus bar diameter divided by 2. Okay, once again, on a test, this is not going to be a mystery. I'm going to give it to you. Here we don't know, so I'm going to assume a number 4 bar. So here, I'm going to assume a number 4 bar. So if I do this, I've got T is 8 inches, cover is 3/4 of an inch, and a number 4 bar is a 1/2 inch, and 1/2 of a 1/2 is 1/4. So D for deflection is 7 inches. Is 7 inches bigger than 3.19? Yes, it is. Therefore, this number is good. I validated it. We're going to use 8 inches for our thickness. So part 1 is done. We found the thickness based on deflection. We checked it based on bending, and we found out the deflection controlled. And now we've got a thickness of 8 inches. So, given that now, we continue on, and we try to figure out the type of steel we need. Okay, type of steel. Let's go. We just finished letter I. Choose the largest of the 2 thicknesses. 3.19 versus 7. 7's biggest, so we got her. Okay, so we're going to go to J. J says, if you selected based on deflection, then D is larger than required for a balanced section. That should make sense. Therefore, AD in the table, page 423, needs to be reduced by the following method. So, letter K. So I'm going to go to the table and find AD. AD. So I've got 40 and 3. So I'm going to go to page 423, go to 40 and 3, and AD is 0.685. 0.685. The next is reducing. So we've got a too big section based on bending. So letter K says AD revised. AD revised is equal to AD in the table times T in flexure in step H over T in deflection step A. So what do I got? I've got D down here, 7 inches. Okay? And I've got what here? D, 3.19. That's letter, if you follow it through, I've lost a little bit here. This is actually F, G, minimum D, H. I'll write H right here. That is D star is equal to 3.19. So I need H over T, 3.19 over step A. Ooh, I think I made an error here. Okay, I've got T. T T in step A is 7.68. And T over here is what? Right here, I need this T. To get T, what do I have to do? Add cover add the cover, add half a bar diameter, so T in step H is 4.19. Therefore, T equals 4.19 inches. 4.19 goes right there. Now this is the confusing part a little bit for students. Remember not to throw this away because it goes in the bottom of that equation in step K. And then also remember that we're dealing with T's, not D's. So when you get to this one and figure step H, make sure you add the bar diameter and the cover, half bar diameter and cover to the number. So let's do the math. There's my AD revised. What are we doing here? We're actually reducing the steel because the concrete section is too big. Same as we did before. So let's clear it. I got 4.19 divided by 7.68. And I'm going to take that and I'm going to multiply it by 0.685. And I get 0.374. Okay, that takes care of step J. K is 3.74. Let's finish up K. A revised equals AD revised times D, and D is right here, 7 inches. Okay, 3.74 times 7. 0.374 times 7. 0.374 times 7. 2.62. I need that number. Okay, so there's some numbers on this board that I really need to keep track of. One is this guy. One is this guy. One is this and this. And the other is this over here. Okay, so make sure you've got a handle on where those numbers are. This gives me the moment. This gives me the thickness actual. This is the rounded thickness. On a test, you will be using the actual as the rounded. This gives me the D versus the T, and this gives me the D required for flexure and the T required for flexure. So we're in pretty good shape. Okay, the next step is about the end. The end says L, the area of steel. So we're still in the main steel. The area of steel is equal to the moment, 139. This should be an equation that looks kind of familiar to you. Fy, we were 40.